Please welcome Alexandros Bantis from Tubi, and this is our opportunity to find out what really does Tubi do behind the scenes. His talk's going to be on scaling up ML experimentation at Tubi fivefold.
So I'm going to talk tonight about scaling up ML experimentation 5x and beyond. So basically, I want to talk about how Scala is helping Tubi to become a data-driven organization. And so specifically, two projects. So the first one is ranking service, which serves up batch compute recommendations to personalize the user experience. And then the other one is Popper Engine, which schedules and runs ML experiments. And so ranking service has been in production since the beginning of the year, and we've helped to scale up the velocity for the ML engineering team by 5x. And Popper just came online for us maybe about a month ago, and it should increase it many times more. So my goal tonight is to kind of talk about some key things that have helped it to be successful. And so I'm hoping that there'll be some interesting things in there for you. So before we get started, let's talk a little bit about Tubi. This is the home screen that you see when you first land. People go to Tubi to watch movies for free. No sign up, no subscription, no credit card. You just go there and you can watch it. So we have over 1,000 advertising partners. We have over 200 content partners. We have over 15,000 titles and over 20 million active users. So the problem. So according to a study by Netflix, people will spend about a minute trying to find the title that they're interested in. And after about a minute, then they just give up. So personalization helps users find the title that they're interested in as soon as possible. So that's kind of like the core thing that I'm working on. So here's our home screen. What we want to do as much as possible is move recommendations left and up. Right? So our goal is everything that we think the user is going to want to see, we want to shift up to that part of the screen. So that's kind of our problem that we want to solve. So this is kind of the old way of doing things. It was built on Node.js and Redis. So the experiment engine over here uses Facebook's Planout to run A/B experiments. Analytics receives experiment results. Redis is a persistence layer and also an data interface to the homepage service. So the homepage service is what builds that home screen that you see. So in order to run an experiment, the homepage gets a request, and then it makes a call to the experiment service and says, okay, what do you want me to do? You want me to go left? You want me to go right? It gets a response from the experiment service. It fetches what it needs to from Redis. Then it delivers the results to the client, and it publishes an event to analytics. So to run A/B experiments, the ML engineer, so first they got to actually create the model in that Spark data pipeline. And then you publish it they would push it to Redis. And then you got to update the code to the homepage service in order to run the experiment. You also have to update the configuration of the experiment engine, and you got to restart both of these services in order to run the experiment. So maybe it's time to upgrade. A lot of these applications were built when Tubi was a small, scrappy startup. A lot of choices made at the time that made very good sense. Maybe right now they don't make such good sense anymore. It's time to revisit some of these things. So we had the usual suspects for upgrading. Better fault tolerance, lower latency, throughput, more maintainable code. But actually in this case, they weren't the catalyst for change. So we had a people problem because every experiment was an endless cycle of please and I'll get right on it. So every time an ML engineer wanted to run an A/B experiment, they had to ask back-end engineers to make code and configuration changes, and this created PRs and tests and code reviews and testing out in staging and deployment windows. And this is for a team that already had their own work to do. So this is the new way. Personalization is extracted out of the homepage service because homepage service does many things in order to assemble that homepage. The personalization is just one tiny bit of that. So that was extracted out into ranking service. So now the ML engineer pushes pre-computed rankings to Redis and then ranking service ingests them. It uses it to handle a request from the home screen. The experiment engine was replaced by Popper engine, which not only runs A/B experiments, but it also have a UI and you can schedule experiments into the future. And of course, the new system is more fault tolerant, has lower latency, higher throughput, more maintainable code. But the biggest win is that the data engineer doesn't have to ask anyone to get right on it ever again. So to run A/B experiments again, they just create the model, publish to Kinesis, and update the UI. That's it. And so they lived happily ever after until the next feature request. So there are a lot of things that contributed to success with this. So we have testing tools like Ammonite and Docker and Akka. We actually use Akka to load test Akka. Scala is just, and I hope I'm preaching to the crowd here, but Scala is just an awesome language that makes immutability easy and is functional, is object-oriented. ScyllaDB is a wicked fast C++ rewrite of Cassandra. And gRPC and protobufs is just very performant. Serialization is much, much faster than JSON plus compression, and you get a certain level of type safety also with it, and Akka as well. So I could talk about all these things, but I want to focus on just three things. Domain modeling. I think this is an area where Scala really shines. ScyllaDB, which has been a big win for us here at Tubi. And Akka, the good parts. So let's dive into domain modeling and ranking service. Again, it's used to doing pre-computed rankings that it's getting from the data pipeline. So the foundation of this is an ID. It's a string value, and it has an enum of ID type. And this we kind of have because of gRPC and protobufs. So we have a lot of different systems here: iOS, Android, ITT, OTT. Like for each one of them, they have a different idea of what an ID is. Some is string, UUID uppercase, UUID lowercase, integer. So we just unified everything as a string. And a target represents a non-empty set of IDs. So we can do things like, we can not only express the idea of a device ID, but we can express the idea of a target as being a set of device ID and, say, platform, or device ID and user ID. Just lots of different combinations. So a ranking contains three parts. It contains data, metadata, and the target. And the model state here is really the key thing, because we have a way of expressing within the domain that something is either in the release state or it's a candidate to be experimented. And so ranking service saves these based upon the target, and then also either its release or it's the model name. And so the result is that we don't have to do any code changes in order for data science to do new experiments. They don't have to tell me at all. I only kind of learn about it after the fact. So here's the protobuf. Again, it's like a very simple, and the kind of simplicity here basically has allowed us to use the same kind of model. And we've had a lot of changes during the year, and we've really had to change the actual API. We've made almost no changes at all. So that's really helped us to keep down the amount of code change that needs to be done in order to handle new features. So this is this is kind of small, sorry. So this is like an actual ranking class. And basically we have to extend this idea of a ranking, and we have to implement one function, and we have this new set of functionality. So, and again, this is kind of like the database schema. It's a very similar. So when we have a new type of ranking that needs to come online, we basically have to maybe implement a new ranking function, create a new table in the database, maybe a few other changes, and we're good to go. And because everything is very strongly typed within the system, there's no strings or ints, the compiler really gives a lot of support as to making sure that we're making changes in a very safe manner. So again, I think that like this is where Scala really shines for me, is just the ability to take some domain and express it with great clarity and precision. And the compiler and maybe some tests are going to really help make sure you're not doing anything crazy. All of this could have been done in any language, but the best, I really strongly believe that the best way to do this kind of stuff is with Scala. So far as the persistence, we considered a lot of choices. So SQL is very mature. It provides a lot of structure. In our case, though, we're storing a protobuf binary of a ranking. We already get that structure from Scala, and from protobufs. So we also looked at MongoDB. And we use MongoDB here. It provides a very rich query language based on JSON. So there are scaling limitations here in terms of writes because they all have to go through the master node. Redis is used extensively at Tubi. We have a lot of experience with it. It's simple. It's fast. There are scaling limitations with it in terms of writes because they all have to go through the master. Okay, so in terms of Redis, the things is that you have to do extra work for high availability and disaster recovery, and it's limited because it's all in memory. So we needed a solution that would scale to hundreds of millions of writes per day, have very low read latency, high availability, disaster recovery, and Cassandra ticked almost all of the boxes, but it's not known for high performance reads. Typically, you would add a caching layer, maybe a cache warming service as well, or you would make your application stateful. And so this would have become an Akka cluster. So we ended up going with ScyllaDB. So why? Well, one thing is that it's the same as Cassandra. It's the same CQL language, the same tools, same storage format, the same drivers. So that creates a lot of simplicity, which for us is an important thing because I'm the development, I'm the DevOps, I'm the SRE, I wear a lot of hats. So to the extent I can use a tool that helps me to be more productive, it's a big win. So it's the same, but it's also more simple. So don't get me wrong, I understand how to tune the JVM. But again, we don't really have an infrastructure team here, so I would really prefer to spend my time building things rather than tuning big clusters of database. So it has a smaller footprint, which is also very nice. You can run ScyllaDB on basically the largest possible instances that AWS has. And you can get 100% utilization out of that. So what that means is I'm never going to have to be spending time in front of a dashboard managing 30, 40, 50, 60, 70 instances. It's always going to be a cluster of 3 instances. As the needs grow, all I need to do is scale up the size of the instances. And then finally, in comparison to Cassandra, we have a bunch of init scripts that will do all of the kind of tuning and configuration for you. And like their philosophy basically is that any kind of setting a machine or script can figure out what is the correct value at runtime at when it's first being installed, or maybe it shouldn't even be configurable and the system can just tune it automatically. And again, the biggest win is that it's faster than Cassandra for the reads. So right now, I have a node of 4 instances, and they handle about 100 million writes per day from batch jobs generated in Spark and Airflow. And at peak, they're processing about 20,000 writes per second. And even at that load, the performance is really good. The average is about 400 to 600. So during peak load, the performance will jump to about 600 microseconds on average. The P95 will jump to about 1.5 milliseconds, and the P99 to about 6 milliseconds. And we're working on bringing this down. And incidentally, like, one of the reasons that the average is fairly low is because ScyllaDB has their own caching built into the system. So that's why when you're doing this, you don't need to implement a caching solution, because caching, in-memory caching, is kind of built into the system. So, like, what's the secret sauce for it? So Scala uses a shared heap, and that's one of the great things, is because of that shared heap, immutability becomes very simple, because you have all of these pointers that you can pass around. And so immutability becomes much less expensive. But there are problems. You can't just throw more threads at a problem. It doesn't necessarily scale well. In Cassandra, each JVM is a node in the cluster. In ScyllaDB, each CPU is a node in the cluster. So there's no context switching, there's no contention. Each node of the cluster is an asynchronous process pinned to exactly one CPU. And if you have other processes running on the machine, at startup, you would make sure that there's, say, 1 or 2 CPUs that are dedicated to other stuff running on the OS. So queues are a fact of life. We can't escape them. It's just a question of where we want that queue to live. So in Scala, uncontrolled futures result in runnables queuing up inside of a priority queue of an executor service. And all of these solutions, Akka streams, ZIO, Scala Z task, they're all about moving that queue closer to the application, so that we can do intelligent things like cancel a task that's been queued up for too long. The same problem exists with Cassandra. It relies upon queues in the kernel space. So Scylla has all manner of schedulers that prioritize some tasks over others, can cancel tasks, can do all manner of slicing and dicing to make things more performant and as safe as possible. So it's just a really nice, it's been a big win, again, because I was able to keep my applications very simple as stateless applications. So at Tubi, we make use of type-level libraries like cats, but we're an Akka shop. So Akka introduces some level of complexity because the developer needs to think across 3 different paradigms: object-oriented, functional, and also actor-based. And that can be a little bit scary. We can use Akka streams, but while it abstracts away the actor paradigm, it also introduces yet another DSL. So let's take a peek at Popper Engine and see how just plain dumb old actors, nothing fancy, can add value and manage complexity. So recall that Popper Engine is a place where the ML engineer can schedule experiments and run experiments. It's very fast. It has a P99 of 3 milliseconds, And it's fast because of the simplicity. So a namespace is a place where experiments can run with certain guarantees. It has state. So there's experiments that are running within the namespace, ones that are running now, and ones that are going to be scheduled in the future. And it also has segments. And these basically represent a claim of allocation of the space. So say that it's the namespace of all users who use the Android Tubi app. So the more segments that an experiment has ownership of for the time it's running, the more people are going to participate in the experiment. So this is the bare bones interface of the namespace class. The namespace is immutable. It's an immutable state machine. And so the API, this is again like a very simple version of the interface. It expresses like two calls. So one is you can evaluate. Evaluate is very simple. In most cases, you're just generating two hash values, and you're using them to do array lookups. And update, on the other hand, changes the ownership of the segments. And so experiments that are going out or coming in, or they're changing phase. Now, the fact that namespace is immutable provides very good guarantees. But concurrency is tricky. And anybody who tells you otherwise, I've got a bridge that I want to sell them. So what do I do? So I could introduce concurrency into the class so that it would regulate its own state. But then in that case, it's no longer immutable. I could, what else could I do? I could just put all of this state inside of an actor. And then I don't have to worry about that. But then I could have made namespace an actor. But both of these approaches are not satisfactory to me. So namespace is a very complex business logic, and I would need to mix functional and object-oriented and actor kind of paradigms together in the same space, and just thinking about that gives me a headache. I don't want to go there. So instead, what I'm going to do is I'm going to have a separation of concerns. So so I'll have one that is object-oriented. So the namespace implementation class is object-oriented. It's an immutable class. The namespace companion object is going to be purely functional. So no side effects, referential transparency. So everything that I can possibly put into the companion object, I do, so that I can do this space that's purely functional, that gives me very strongly typed methods that I can use to help me actually execute the business logic in the object-oriented class and help me manage state. So it's referential transparency, strongly typed, all these things that provide value from functional programming. And then, so here's a bare bones namespace actor. So there's no functional programming here. There's no object-oriented paradigm. It has no business rules. Its only purpose is to provide a safe and simple context for the namespace class. And really, as actors go, it's quite dumb. And I like working with dumb actors because it helps me sleep at night. So, as in conclusion, the core problem that needed to be solved was people. We used engineering to solve a people problem, not a process problem, a people problem, and that's really great when you get a chance to do that. We helped another team become very, very productive. And we did that primarily through good domain modeling. We could have done that in any language, but Scala, because of value types and algebraic data types, easy mutability, object-oriented, functional is like a perfect fit for that. So ScyllaDB is a great tool to have in the toolbox. For ranking service, it allowed me to use fewer components, not have to not have to deal with the complexities of having a stateful application, and it's been very, very stable and reliable for us. And finally, Scala is a polyglot language, which is both a strength and a weakness. So having a clear separation of concerns, object-oriented code in classes and functional code in companion objects, and actors where necessary, just providing the illusion of synchronous programming is a big win. And these are some of the key reasons why Scala, ScyllaDB, and Akka, they're helping Tubi to become a data-driven organization. That's it. Thank you.
Questions?
Is there like a high-level library to get to these databases, to Cassandra and Scylla, or do you have to do low-level calls to the database? And is it Java or is it Scala specific?
So it uses Cassandra drivers. So you could just use whatever implementation you feel most comfortable with. There are there's Java. There's the DataStax Java driver. There are Scala wrappers of that, and actually Scylla has a fork of it as well. So whatever libraries you would use with Cassandra, you can use with Scylla as well.
Any other questions? Great, just... Question?
Is plan out still in the picture?
So we are not using it. So basically with the system that we have right now, the experiment engine, it works as both a scheduler. With plan out, when you want to start running a new experiment, you need to update the configuration. Yeah, so right now I have Hopper Engine is running in production right now, and it knows experiments weeks in advance. So they're already there. I don't have to do anything. When, at midnight of whatever day when the experiment goes live, it'll just go on. I don't have to do anything.
So I'm sure that anybody who's working with kind of data models like you have is going to see that you don't have uniform data analysis. Like you're going to have a Zipfian distribution where some shows are far, far more popular than others. How is like that kind of Zipfian distribution impacted your system performance?
So we haven't had any problems. So there's been like a couple of small incidents so far this year, but in every case, it's been a people problem. It's been me. I pushed code that wasn't 100% ready, but ScyllaDB, I've had zero downtime from it, and the application has just never gone down. I've never lost any data. It's just always there.
Questions?
You framed this as solving a people problem where you kind of cut back-end engineers out by letting data scientists do things directly. Do you ever have problems where things became too easy for the data scientists and there was sort of a, you found you needed the back-end engineers to make sure that the code was, not going to consume too much resources or something else? I don't know. So
I think like the philosophy that we've tried to have is that so what we do is very hard. It's not easy. Conducting an experiment is not easy. You have to make sure you're answering the right question. You have to make sure that you're measuring things correctly. You have to make sure that the different systems can synchronize with each other. There's so many things that can go wrong. And so you need to be able to focus your mind on quality. So I've been a big advocate at our organization of Scala Fix, Scala Style, Scala Format, because I don't want to spend my time with code reviews talking about minutia. I want other people to think about my code to find out if there are any quality issues, if it's actually going to work as intended. And that's kind of been our objective here as well, is in the same way that Scala Style and Scala Format takes your mind away from these little details that are just a distraction, Popper Engine and all these different systems are not there to make it super easy to run crappy experiments on the fly. They're there to ensure that we don't introduce friction, and you can, and the data engineers, the application developers can focus on creating quality experiments.
Any more questions? Great. Well, thank you all for coming tonight. Tubi are recruiting, so please thank them by going and seeing them and saying you want to work for them, all right? And if you're too shy to do that, come and see me and I'll introduce you to them. Thank you so much. And before you all go, next week we do have more talks for you. We are at Twitter's RSC team, who are, I believe, working on an open source fast Scala compile project called RSC, which I don't know much about, are going to be talking about that product. The creator of Metals will be at that event, though I couldn't convince him to do a talk, but maybe you can all convince him on the day. So yeah, please come and meet Olaf at the next week's Twitter event. Thank you so much. Thanks for coming. Thank you. Bye now.